Hello, everybody. Today we're going to start Unit 5, which is all about momentum. So the lesson today is topic 5.1 about momentum and impulse. So let's fill in some notes. First definition is going to be momentum, and I'm just going to give you a formula for that. So the symbol for momentum is a lowercase p, and it is equal to mass times velocity. And since we're dealing with vectors here, I'm going to give little vector symbols. Awesome. So something with momentum, it can have more mass. So if you imagine a bunny rabbit versus an elephant, they're both coming at you with the same speed. The elephant has more momentum. Okay? Similarly, let's say you had two cars driving. If they were the same mass, but one was going faster than the other one, then that faster car would have more momentum. So momentum is affected by both mass and velocity. Okay. Momentum has the same direction as velocity. Okay. So momentum is a vector, it has the same direction as the velocity. Okay. The unit, unfortunately, doesn't have anything cool. It's just the unit of mass, which is a kilogram, times a meter per second. So kilogram meter per second is the unit for momentum. Okay. To change the momentum of something, we have to change the velocity. So to change the velocity of something, there needs to be some sort of force. Okay. So force is required to change momentum. So kind of a cool thing, Newton's second law, which is something that we learned about in our first unit, which is sum of forces equals mass times acceleration. This is actually a later version of Newton's second law. It was originally based on momentum. So if we think about the definition of acceleration, we can change this into sum of forces equals mass. Acceleration is just a change in velocity over change in time. So I just substituted the definition of acceleration in here. Okay. And if we look at this top part right here, mass times a change in velocity, that's just momentum, specifically a change in momentum. So Newton's second law can be written as the sum of forces equals the change in momentum over change in time. Cool. So essentially, force is the rate of change of momentum. For you calculus people, force is the derivative of momentum with respect to time. Cool. Right. Next definition is impulse. We're just going to rearrange that Newton's second law to look like the sum of forces times the change in time equals a change in momentum. So this idea right here, force times change in time, which is just a change in momentum, that is the idea of impulse. For us, we're just going to use force times change in time, but in some textbooks, you'll see that written as a J, capital J for impulse. So if you ever see that, that's what it's talking about, but you won't really run into that in our class. So the idea of impulse, let's say that you are running, okay? So you have mass, you have some velocity, and you run into a barrier, okay? So if you run into a brick wall, you're going to be going, with some velocity, and then you're going to stop. Okay? So imagine running into a brick wall. You're going to stop pretty quickly. That's going to have a really, really small change in time. So small change in time, you're going to end up with a larger force if we have the same change in momentum. So running at a wall, you go with some momentum, then you stop. You have a change in momentum. If that happens over a small period of time, you're going to have a larger force. Okay? But imagine instead I put a bunch of marshmallows right here. Okay. With the marshmallows, you're still going to have that same change in momentum. You're running and then you stop, but the marshmallows will cause a larger change in time. It's going to take a larger amount of time to stop. So that means it's going to overall be a less amount of force. Okay? And so don't try this at home, but imagine running into the wall versus running into a big pile of marshmallows. Which one's going to feel nicer? It's going to be that one that has less force. Another thing about impulse, we love graphs. So if we have a graph of force versus time, okay, let's say we had a constant force being exerted over some amount of time, the area under this curve is the impulse or the change in momentum. And so in a real life situation, what that might look like, so let's say we have running into the different objects. So if you were running and you ran into a wall, that force might look like a big spike. Okay, so this is running into a wall. Okay. But then if you ran into a bunch of marshmallows, that graph might look something more like this. Okay. And there we go. What would be the same about these two graphs is that they would have the same area because both of those scenarios have the same change in momentum. All right. Force on a system. So let's say we have a system of multiple objects. The change in momentum for the whole system is going to be equal to the sum of any external forces times change in time. So it's just the same sort of impulse equation, but now specifically for a system of objects and an external force. So only external forces change momentum. So if we have the sum of forces external equal to 0, we're going to have no change in momentum. And what that is considered, that's called a closed system. So let's do some examples. First example, we have a 4 kilogram ball rolling 8 meters per second. So 4 kilogram ball traveling 8 meters per second. It is hit with a 40 Newton force 4.5 seconds in the opposite direction. So a force is going to be applied in the opposite direction, 40 newtons, for 0.5 seconds. Okay. What is the new velocity? Okay. So for that one, let's use my change in momentum equals force times change in time. A change is just a final minus initial, so let's replace that with final momentum minus initial momentum equals force times change in time. I know that momentum is mass times velocity, so let's replace those. So mass times my final velocity minus mass times my initial velocity equals force times change in time. There you go, forgot the V. Awesome, so let's just rearrange that to solve for what we need. We're trying to find the final velocity, so let's add that mv initial to the other side. And I know the mass is 4 times my final velocity equals 40 in the opposite direction. So make sure that's a negative 40. Negative 40 times 0.5 seconds plus 4 kilograms times 8 meters per second. Add those together, divide by 4. Our final velocity is 3 meters per second. Cool. Right. Next example, we have a cart that has a mass of 2 kilograms is initially traveling to the right at 4 meters per second. Next external force. Cool. Similar problem. So why don't you guys work through that one? And I will, let's see, put the answer up here. See if you can get the final velocity to be -4 meters per second. Cool. All right. Next one, we have a graph. Okay. So, similar idea. We have a cart A with 2 kilograms. It's traveling to the right at 4 meters per second. A variable external force, that just means we have a changing force, as you can see by the graph, is applied to the cart over a time of 4 seconds. Positive forces indicate a force to the right, so I'm assuming that the negative force is to the left. Calculate the velocity after 4 seconds. So what we know initially, we know that our initial momentum is 2 kilograms times 4 meters per second, or 8 kilogram meter per second. Cool. So what we need to do is figure out the total change in momentum, which I can find from the graph here. So the area under here, okay, that's a triangle. Okay, so that's, and it's negative. So my change in momentum there is -1/2 2 times 20, okay, which is -10. Right? Yeah. No, it's not. It's -20. Sorry. Half of 2. Okay. And then plus, over here we have some positive change in momentum. So here we have 1/2 times a base of 1 and a height of 10. Okay. So that's +5. And then this area right here is just a rectangle. 1 times 10 is 10. Okay. So that gives me a total of -20 plus 15. -5 is my change in momentum. So we're trying to figure out the change in momentum. Okay, blah, blah, okay. Change in momentum is my final minus my initial. I know my initial is 8, and my change in momentum is -5. So -5 equals my final momentum minus 8. Add the 8 over. 3 equals my final momentum. And momentum is mass times velocity. So you take 3 and divide by 2 kilograms to get my final velocity of 1.5 meters per second. All right. And the last example. A system is comprised of 2 objects. Okay. We have a 4 kilogram object moving 2 meters per second to the left, so -2 meters per second, and a 12 kilogram object moving 4 meters per second, also to the left. So ignore that. It's also to the left. Okay. All right, so then after 2 seconds, the 4 kilogram object is moving 4 meters per second to the right. And the 12 kilogram object is at rest. Cool. We know the change in time is 2 seconds. So let's figure out the magnitude and direction of the net force. So that's the total force that was acted on this system to change the motion. Okay. So remember that force external equals times change in time equals my change in momentum for the system. So from this first part here, I can figure out the initial momentum just by adding the momentum of the 2 objects together. So this first object has a momentum of -8, and this one has a momentum of 4 times 12, 48 negative. So my initial is negative 56 kilograms meter per second. The final momentum for this system, this has no momentum because it's not moving, and this has positive 16 kilogram meters per second, just 4 times 4. So 16 kilogram meters per second. So here I can look at my change in momentum. So my change in momentum equals final minus initial, 16 minus negative 56, which equals my force external times my change in time, which is 2 seconds. So if we take 16 plus 56, divide by 2, our external force is 36 newtons.